You, Tom, for accepting the invitation.
Yeah, thanks for having me.
I would like to very fast introduce you. I would just few words. First one, so you did your PhD at the University of British Columbia in Canada, and then, if I'm not mistaken, you had the postdoctoral appointment with University of Cambridge, and since 2021 you are professor in Caltech in the US, right? So, yeah. So the contribution of your talk, which is really interesting, has the title "Critical Behavior in Long Range and Hierarchical Percolation." So please, Tom, go ahead.
Great, thank you, and thanks everyone for coming. Thanks for inviting me. So I'm going to talk about long range and hierarchical percolation, but I want to start by talking about the more classical case of nearest neighbor percolation and discuss, what we know, what we would like to know about nearest neighbor percolation, and how these questions can actually be easier for long range percolation and then easier again for hierarchical percolation, and what the relation is between all of these things. Let me start, and I should say that when I've given this talk before, I end up spending most of the time sort of discussing the conjectures and the results, and not having very much time to talk about the proofs. Hopefully I'll have a little bit of time to talk about the proofs, but I have a lot of additional material prepared, which I probably won't have time to go through. So if at the end you want to know more, I'd be happy to tell you about some of the other stuff. Okay, so first of all, what is percolation? So the classical model of nearest neighbor Bernoulli bond percolation. So we start with the hypercubic lattice, right? So the strings of length d of integers which represent the vertices, and where there's an edge between two vertices if they differ by 1 plus or minus 1 in exactly one coordinate, right? So that's the lattice ZD, and when we do Bernoulli bond percolation on it, all we're doing is flipping a coin independently at random for each edge of the lattice. It has some probability p of being a head, and every time we see a head, we keep the edge. Every time we see a tail, we delete the edge, right? So we're just independently keeping or deleting edges with probability p of keeping the edge, right? And the standard sort of jargon in the field is that the edges we keep are called open and the edges we delete are called closed. And generally speaking, we're interested in the geometry of the connected components of open edges, and these are referred to as clusters. Okay, and one of the basic definitions is that you have PC is the infemal value of P such that infinite clusters exist. Okay, now the existence of an infinite cluster is a tail event. So by Kolmogorov, it has probability 0 or 1. So PC, when you're above PC, infinite clusters exist with probability 1. When you're below PC, they exist with probability 0. Okay, and this talk is really going to be about critical percolation. So it's going to be about what happens exactly at this point of phase transition. Okay, and one of the basic facts is that PC is strictly between 0 and 1 when the dimension is 2 or higher, right? This is a consequence of the classical piles argument that was originally done for the Ising model. It's actually simpler, if anything, for percolation. Okay, of course, in one dimension, there are fairly obvious reasons why you don't have a phase transition. So the model is not very interesting in one dimension. Okay, and I should say there are lots of interesting questions about percolation away from criticality, but I'm not going to be addressing those things in my talk. I'm going to focus very much on the critical case. Okay, so there are kind of a few basic things that we would like to, or basic and not so basic things we would like to understand. Critical percolation is very hard, right? One reason it's hard is that, okay, so 2 dimensions is very special because for many lattices, you can exactly compute PC. And although the model is not exactly solvable in the way that sort of the 2D Ising model famously is exactly solvable, it nevertheless has a lot of special features, and you can kind of argue about it very directly. in dimensions other than 2, you're not going to know exactly what PC is. It's only going to be defined implicitly as this point of phase transition. And generally speaking, proving things about critical percolation is very difficult. So the most basic question you can ask about critical percolation is, well, it's defined to be this boundary point between when infinite clusters don't exist and when they do exist. So do you have infinite clusters at the critical point or not, right? And basically, it's believed that you do not have infinite clusters at the critical point in any dimension, but this is only known in 2 dimensions and in high dimensions, and establishing this particularly in dimensions 3, 4, and 5, and 6. 6 is a little bit different, but this is a problem that people just don't really have good ideas of how to approach yet. So it seems sort of beyond the scope of existing methods. Okay, now, although I've just spent all that time telling you about how hard this problem is, this talk is not really going to be about that problem. It's going to be about the things we would like to do after we understand that. And, you know, and we would like to really understand this phase transition in a more quantitative way. Okay, so these are questions about critical exponents and about scaling limits. Okay, so let me start by talking about critical exponents. So, you know, this is a very general belief coming from the physics literature that models undergoing continuous phase transitions should have lots of interesting kind of scale-free behavior. And the fact that this behavior is scale-free kind of forces things to have power laws. Okay, so it should be that various things, for example, if you look at the tails of interesting quantities at criticality, or you have some quantity that blows up or goes to 0 as you approach criticality, often these things will decay or grow in a way that's described by a power law. Okay, and so a few of these that will play an important role in this talk, it's mostly these first 2 actually. So these exponents will have these kind of traditional notations for them. So there's eta, which is defined so this means the probability that x is connected to y at PC, at criticality. So this should decay like a power of the distance between x and y. And the traditional notation for this power is minus d plus 2 minus eta. Okay, and the reason it's written this way is that in high dimensions, you expect that the connection probabilities decay like the Green's function, and the Green's function decays like minus d plus 2. So eta equals 0 is like Green's function decay. So eta is like the correction to having Green's function like decay. Another exponent that will be important to us is delta, and this is the tail of the volume of the cluster at the origin. So I'm going to write just k, or sometimes k sub 0 for the cluster at the origin. So this is saying the probability that the cluster at the origin has at least n vertices should decay like some power of n, and this power is traditionally denoted 1 over delta. Okay, another one, just to give an example of something that's off critical rather than critical, is gamma. So it's known that if you look at the expected size of the cluster at the origin, this is finite below PC and infinite at and above PC, and it's expected to blow up like a power as you approach PC from below. Okay, and this power is gamma. Okay, and of course, anyone who's worked on these kind of things before will know this, but it's important to stress that the existence of these exponents is not, it's certainly not something that comes for free. And generally speaking, it's very hard to argue that they exist without actually computing them or proving that some scaling limit is well defined. So those are so generally speaking, proving these exponents exist at all is kind of on the same difficulty level as all the other really hard things that we would like to do. So even just to start off with, we certainly don't know that these exponents are well defined. Okay, now so one of the really interesting features, and again, this is something that happens very broadly in statistical mechanics, is that there are 2 things about what these exponents depend on. So one of these things is universality. So the idea of universality is that if we look at sort of different grids in the same dimension, like, for example, if I look at the square grid or the triangular grid in 2 dimensions, all of these exponents should not depend on the choice of grid, provided that the dimension is fixed. Okay, of course, this is something we don't know how to prove at all, but, you know, it's probably true. And, you know, we have some kind of conditional proofs in some situations, particularly in 2 dimensions. On the other hand, the dimension is very important. Okay, so even though the choice of lattice of a given dimension shouldn't be very important, the dimension certainly is. And turns out the easiest case to understand is the high dimensional case. Okay, so for percolation, high dimensions should mean that the dimension is strictly larger than 6, although, you know, current methods need it to be higher than that, but this strictly larger than 6 is where we expect all this high dimensional phenomena to hold out. So 6 is what's called the upper critical dimension for percolation. And the idea, broadly speaking, and again, this is something that happens in all kinds of models, not just percolation, like, for example, the Ising model has the same kind of thing, but there the upper critical dimension is 4. In fact, 4 is a very common value at the upper critical dimension. Percolation is a bit unusual that it has 6 instead. Okay, and the idea is that once you're above this upper critical dimension, the lattice is kind of so spacious that the model starts to behave as though there's no geometry at all, or that, you know, it kind of behaves the same as it would do if it was on a tree or a complete graph or something else, where it's not really feeling this finite dimensional nature at the lattice. Okay, and in particular, this manifests itself through these critical exponents taking simple values, which are the same values they take on the tree or the complete graph. And of course, percolation on the tree is just like a branching process, and percolation on the complete graph is the Ödel-Schwenny random graph. So, you know, these 2 things are both very classical. So in particular, if you look at the probability that the cluster at the origin has at least n vertices, that behaves like the total progeny of a critical branching process. So it's a 1 over root n tail, which means that this exponent delta should be equal to 2. One thing that this, it's a bit confusing if you think about the high dimensional behavior. So by the way, this high dimensional behavior is called mean field critical behavior. This terminology comes from the Ising model, because if you do the Ising model on the complete graph, it's like you're interacting with the average of the field, i.e. the mean field, rather than with your neighbors. So if you ever wondered why it's called mean field, that's why. For percolation, this doesn't really make sense in the same way, but the name is still used. So one thing that's a bit confusing is how to think about the 2-point function, right? Because you know, this is something where actually you do still get some kind of lattice dependence or something, or I mean, dimension dependence. So really the right way to think about it is that in high dimensions, critical percolation behaves like a critical branching random walk. Okay, and for critical branching random walk, the 2-point function just is the Green's function. So that's why you should expect Green's function-like behavior for high-dimensional percolation. And all this means at the level of exponents is that the probability x is connected to y should behave like the distance to the minus d plus 2. Okay. And, you know, one reason why this kind of makes sense is that you can kind of think about when if you kind of explore your percolation cluster, maybe in like a breadth first search or something, it kind of behaves like a branching random walk, because, you know, you have the sort of frontier of stuff that you just explored, and then each edge in the boundary could be open and will you know, get you something new. The reason why it's not a branching random walk is that, you know, if you return to something you've already seen, then you don't make any new edges. So it's kind of like a branching random walk that gets killed when it visits the things it's already gone to. I mean, it actually literally is that. So the idea is that in high dimensions, this self-interaction of killing when you hit what you've already seen just doesn't make very much difference. So the models sort of belong to the same universality class in sufficiently high dimensions. Okay, and basically this is something we actually understand quite well now. So there was this whole technology developed in the 90s by Hara and Slade called the Lace expansion. Well, it was first introduced by Bridges and Spencer for self-voiding walk, and then developed much more extensively and also extended to percolation by Hara and Slade. And basically they proved that all this stuff is true in sufficiently high dimensions. Okay, so so originally they needed the dimension to be at least 19 or something like that. This is a bit misleading though. So really their proof requires some kind of numerical inputs, like basically the Lace expansion is a way of re-expressing the 2-point function. One way you can think about it is sort of doing inclusion, exclusion, expansion. And you need this to converge, and just to prove this, it helps for some quantities to be small rather than just to be finite, basically. And this gets easier the higher dimensions you're in. On the other hand, as soon as you're above 6 dimensions, their proofs let you say that for some lattices, you have mean field behavior. So maybe not the nearest neighbor lattice, but if you take the points of ZD and you connect up any 2 vertices at distance at most 1 million or something like that, then their proof will already work in 7 dimensions. Okay. On the other hand, once we go below or 6 dimensions or below, this mean field behavior should not hold anymore. So you will not be able to prove anything through these kind of methods because they establish the mean field behavior. Okay. And just to say about the nearest neighbor lattice, currently the record for is D at least 11. So this was done by Pfitzner and van der Hofstad something like 10 years ago. And that involves a lot of like computer assistance and things to kind of optimize down all these constants and so on. Okay, so and I should say actually really the Hara and Slade did some of this, but they didn't really prove this. They proved the analogous estimate for the Fourier transform, and actually proving the pointwise bound for specific x and y was done quite a lot later by I want to say Hara, Slade, and van der Hofstad, maybe in Sakai. Sorry, I should have written that down, but just to say that actually it's quite a subtle issue that we'll return to, that sometimes it's much easier to get bounds on more averaged versions of these quantities, and getting pointwise estimates can be a lot harder. Okay, so one thing I'd like to mention about this high dimensional picture, although we understand things at the level of exponents very well, it's actually not, it's still open to understand things at the level of scaling limits. So the belief is that if you take, for example, take your critical percolation cluster at the origin in high dimensions and condition it to be large, it should converge under appropriate rescaling to what's called super Brownian motion, which is the scaling limit of critical branching random walk, and which is understood very well, and you can understand it very explicitly in terms of SPDs and so on. But this has not been done. There are some things that have been done. For example, proving that the what's called the spine of the cluster converges to Brownian motion, but this actually remains open. Okay, so that's the high dimensional case. Now, on the other hand, when we go to low dimensions, so when we go below the upper critical dimension, the finite dimensional nature of the lattice should start to affect what the model is doing in a non-trivial way. Okay, and in particular, when you're strictly below the upper critical dimension, so when D is strictly smaller than 6, this should really mean that the exponents change and the scaling limits change. Okay, so there's one case of this that we understand well, which is 2 dimensions. So as I mentioned before, 2 dimensions is extremely special. There are a lot of special tools that are specific to 2 dimensions. You have planar duality, you have, the topology of plane curves, like the curves have to cross each other, things like that. You have complex analysis, which is extremely powerful and relevant here. You have related things from conformal field theory and so on. So there are many, many things that are very special about 2 dimensions. And we understand percolation pretty well, at least for some specific choices of lattice. So first of all, this problem of continuity about whether you have infinite clusters at criticality, which by the way, in high dimensions is a consequence of the work of Hara and Slade. I mean, they prove much stronger quantitative stuff, but that is also the only proof that we have of this more basic question that you don't have infinite clusters at PC. In 2 dimensions, there are sort of much easier topological arguments for why you don't have infinite clusters at PC due to Harry Keston, and there are generalizations of this. These proofs are pretty robust. They don't depend much on the lattice. And we also understand critical exponents and scaling limits pretty well, at least for site percolation on the triangular lattice. So in this case, we know that you have scaling limits that are conformal invariant and they're described by SLE and CLE and blah, blah, blah. And also, Harry Keston proved that scaling relations hold. So essentially, we understand this really well. And we also understand the other lattices well, conditional on the scaling limit being conformal invariant. So this is something that is open, but if you prove that, then it must be described by SLE and CLE, and you must get all the critical exponent that you want. Okay, and so this sort of classical feature of the 2-dimensional models is that you get these kind of strange rational values with like large numerators and denominators. And these are related to conformal field theory and things like that, where there are these, there's a lot of algebra hiding underneath this. Okay. And I should say that, these things were predicted a long time before they were proven in the physics literature, especially by Nienhuis, who used what's called the Coulomb gas formalism. So in particular, he predicted these values of the critical exponents for 2D percolation, I think in like the 70s. Okay. So then there are these what I'll call intermediate dimensions. So dimensions 3, 4, and 5. And here it's really sort of a no man's land. So we don't have exact conjectures for what the exponents are. Probably they are transcendental numbers. I mean, just because we have no reason to believe that they're not. We have no idea how one might describe a scaling limit, and there are really just no good tools for studying the models at all. So the main point of what I'll be telling you about in this talk about the long-range models and hierarchical models is like how we can find some models which are not so different from these. They're phenomenologically quite similar, but where there are more tools available and we can actually start to prove things and understand their behavior. Before I start talking about that, though, there's one case that I haven't mentioned yet, and this is the case where you're exactly at the upper critical dimension, so when you're exactly at 6 dimensions. And again, this is something very typical for statistical mechanics models, that when you're at the upper critical dimension, the model does behave differently than the high dimensional model, but only barely. So the basically various quantities, their scaling differs from their mean field scaling by logarithmic factors. Okay. And for percolation, there are concrete conjectures from the physics literature back in the 70s, this paper of SM, Gaunt and Gutman, where they conjectured exactly what these logarithmic corrections are. So, for example, if you look at the probability the cluster at the origin has at least n vertices, well, it's like 1/√n, that's the high dimensional thing, times log n to the 2/7 conjecturally. Okay, and similarly, if you look at the 2-point function, which is the name for this connection to the probability 2 points are connected, this should differ from its mean field scaling by a log to the 1/21 factor. That's the conjecture. Okay. So a few remarks on this. So maybe one thing to mention first is that if you were to look instead at scaling limits, there's again a very general phenomenon that one expects to hold here, which is that the factors that you have to scale by have these log corrections in them. But once you take those into account, you should get the same scaling limits as in high dimensions. So if you scale appropriately, including the right log corrections, the conjecture would be that you still get the super Brownian motion in the scaling limit in 6 dimensions once you put those log corrections in. Of course, this is well beyond what we know how to prove. I mean, we don't know how to prove really anything yet about 6-dimensional percolation, critical percolation. Okay, now there's a few more comments on this and about why this hasn't been done rigorously yet. So one thing is that the way that physicists like to analyze these kind of things is using, renormalization group type analysis. So, basically you want to, and the trouble is that percolation doesn't really fit very well into the way that this is done in the Wilsonian style. So the idea that you should really imagine something more like the Ising model, where you have like a model where you have, spins, like you have a field, basically like random values at each vertex which are correlated in some way, right? And their distribution is described by some Hamiltonian. So, it's like the probability you see some configuration is like e to the minus beta h, where h is this Hamiltonian. It describes the, energy of the system, which is like the relative likelihood of a configuration. And basically in this RG formulation, what you want to do is kind of zoom out and imagine you kind of like average your spins or something over a large area. And you want to say that renormalized system behaves like itself like a spin system that just has a different Hamiltonian. And you kind of want to think about basically getting some kind of dynamics on the Hamiltonians as you zoom out or something like that. This is one common way of understanding what's going on in these things. The trouble is percolation just isn't like that. You don't have a Hamiltonian. You don't have spins. You have this trivial IID stuff, and then you're extracting this complicated geometric information from it. Okay, so as a result of that, the way this has been understood at a non-rigorous level is to not really work with percolation. It's to work with a spin system, which is just kind of posited to have the same critical behavior as percolation, but this is not really totally justified. And it certainly, nobody knows how to do this at a rigorous level. So in particular, the way this Essen, Gorton, Gutman paper works is they really work with what's called the phi-3 model. And this is expected to have the same critical behavior as percolation, but there's no exact mapping between the two models. So, which I should contrast with a different model, which is weakly self-avoiding walk, where there is an exact relationship at the discrete level between weakly self-avoiding walk and a certain supersymmetric version of the phi-4 model. And this has been used, I guess I'll go to the next page. In this case for weakly self-avoiding walk, because you have this rigorous connection to the spin system, you can actually start to implement these renormalization analysis rigorously. Okay, it's really hard. It's a huge amount of work, but it has been done. And, the trouble is for percolation, we just don't know how to do that properly, like to actually get a spin system which is equivalent to percolation. So that's a serious obstacle to trying to approach it in this, for example, the same way that self-avoiding walk has been approached. So there's and I should mention as well, there's another thing people do in physics to get a spin system, which is to, instead of looking at this phi-3 model, what you do is look at the Potts model. Again, if you don't know what the Potts model is, I'll just talk about it for a minute and then won't mention it again. So I'll let you know when you can start paying attention again. So what they do is they look at the Potts model, which has some integer number of states, right? So Ising is the Q equals 2 Potts model. And what they do is that, so when Q is larger than 2, this makes sense as a spin system, and you can apply all your favorite renormalization group type approaches to it. And then you get some answers for what the exponents are and so on. And then right at the end, you just send Q to what you take the sort of Q goes to 1 limit in these expressions that you have. Okay. And again, this gives you answers which are consistent with these predictions that come from the phi cubed model. And they're probably correct, but this is very far away from being any kind of rigorous analysis of percolation. Okay. So good. And maybe I can briefly mention as well that, I mentioned that low dimensions, we have intermediate dimensions rather, we have a much less good understanding of. So one of the standard ways in physics to approach these questions, and that this is something that goes back to the work of Wilson and Fisher in the late 70s, is to think about, well, 6 dimensions isn't too bad. If we're doing things non-rigorously, we can understand exactly what's going on. And so they say, well, maybe instead of trying to understand 3 dimensions, let's try and understand 6 minus epsilon dimensions. And what they're able to do, again, this is all very much non-rigorous, although it has been made rigorous for some other things. For example, Gordon Slade has done some rigorous work on this for what's called the spin-ON model. So you try to expand these exponents in powers of epsilon as you go below 6 dimensions. Okay, but it turns out that even if you're doing things non-rigorously, you're not going to get like an infinite order expansion, because it gets like harder and harder to compute every term at the expansion. They get extremely complicated very, very quickly. But for example, for percolation, there's this expansion. And if you want to see the fanciest versions of this, there's a paper by Gracie from 2017, is the with the most terms in these expansions. So for example, delta is supposed to be 2 plus 2 over 7 times epsilon plus 565 over 6,174 times epsilon squared. And there's a similar thing for eta. Okay, and of course, there's supposed to be infinitely many terms. So a few comments on this. One thing that if I was doing this on the board and you could see the previous page, you may have noticed, is that the epsilon coefficients here, so 2 over 7 and 1 over 21 here, are the same as these powers of the log in the 6-dimensional logarithmic corrections. And this is a general phenomena, that the log powers at the critical dimension are encoding the epsilon order corrections in the expansion. This is something that happens very generally. Another thing to mention is that these expansions are supposed to be divergent. So they're like asymptotic expansions, but they're divergent asymptotic expansions. So even if you were able to compute this to infinite order, it wouldn't really give you a value at in 3 dimensions. Of course, you might be able to extract an exact value by like doing this in the complex, thinking about complex dimensions or something like that, and using Borel resummation or something. I mean, these sort of things seem like so far beyond the scope of what is possible at the moment, that they're sort of science fiction. But on the other hand, what the physicists do is they compute these things to a few terms. And actually, if you're going to plug a value in, you don't want to take too many terms because they are divergent. And then they plug in epsilon equals 3, and they get actually a very good answer for what the critical exponents are that agree closely with numerics. Okay. Good. And so one thing that you may have been thinking this whole time is that, well, isn't this just nonsense? Because I can't take a 6 minus epsilon dimensional model. It doesn't make any sense. But in fact, this turns out to be one of the least serious issues with this approach. I mean, this is one of the things where we can come up with rigorous ways of doing it that make sense. And this is part of the reason to study these long range models that I'm going to talk about now. Okay, good. Okay, maybe before I start saying about that, I think for many mathematicians, if you hear about, oh, I want to do models in 6 minus epsilon dimensions, it's natural to start thinking about models on fractals. So I'll just say that doesn't really work. So I won't go into it further, but that's not the right way to think about things. Partly because in fractals you tend to have like various different dimensions which are not the same, and things like that, and it just doesn't work. It's, as far as I know, that there's no good way of doing this. So whereas the long range models that I'll talk about now are really a very nice way of thinking about these non-integer dimensions. Okay, so good. So what's the idea of a long range model? So first of all, let me define percolation on what I call a weighted graph. So now we have a graph, but we also have a weight function, J, which maps the edges to non-negative numbers. Okay, and we can define percolation on a weighted graph by saying that each edge E is open with probability 1 minus e to the minus beta j of e. So in other words, you can think about having a Poisson process of edges where the intensity of an edge is beta times j of e. Okay, this particular function is not very important. It just has some nice properties that make it convenient to work with. Okay, the point is, the important thing is that if this weight is small, this is roughly beta times j of e, and it's always between 0 and 1, so it's giving us real probabilities. Okay, so in particular, you know, this weighted graph percolation includes the normal percolation where you just take all the weights to be 1. Okay, and in long-range percolation on ZD, what we do is we take the grid and we think of every pair of vertices being an edge. So any pair of vertices can be included in our percolation configuration, but with the j's are going to decay in some way. Okay, so usually what we do is we think of having a function just from points in ZD to 0 infinity, and then setting the weight of an edge jxy to be j of x minus y, right? So this gives us a translation invariant model. Okay, and we also take the function to be symmetric because otherwise it doesn't make sense. Okay, so this is what we call long-range percolation. And usually we're going to be most interested in the case that j decays like a power of the distance. This is sort of the most interesting case for many things where you get something that can really be different from the nearest neighbor model. Okay, and we'll always think about the integrable case, which just means the expected number of open edges coming out of each vertex is finite. If you don't have that, the model can still be interesting, but you don't get a phase transition. You get like, you know, or you always have infinite clusters, so it's less interesting. Okay, good. So, you know, you have all the usual definitions. You have beta c is going to be the infemal value of beta where infinite clusters exist. This is always positive when you have this integrability condition, so we'll focus on this case where the kernel, this j, decays like the distance to the minus d minus alpha, where alpha is a positive number. Okay, and the reason to write it this way, well, one reason is that it agrees, which will become obvious to you later on with the usual notation for like Levy processes. It's you should think of this alpha as being the same alpha in the alpha stable Levy process, if you know that stuff. If you don't, doesn't matter. And also, you know, this alpha being positive is precisely the condition you need for this to give you something integrable. So that's why it makes sense to work with powers bigger than d here to get the integrability. Okay, and as in the nearest neighbor case, we always have a phase transition when it's not one-dimensional, but in fact we can now have phase transitions in the one-dimensional case as well. So basically we get that if the dimension is bigger than 1, we always have a phase transition. Beta c is always finite. Whereas if it's equal to 1, we have a phase transition when alpha is less than or equal to 1, and you don't have a phase transition anymore when it's bigger than 1. Okay, now it might seem that this model is sort of more complicated than the nearest neighbor model, but the surprising thing is that we actually understand it significantly better than than nearest neighbor percolation in many cases. Okay, maybe we don't understand it better than the 2D models, for example, where things are understood very well. But in many cases, we understand this much better. It tends to get easier to understand the smaller alpha is. So the smaller alpha is, the more long range it is. You know, the decay is slower. And the more long range it is, the easier it becomes. Okay. Maybe one thing I should mention is that, okay, there's something one often sees in the literature, and I want to mention it, but also tell you that it's completely wrong. Well, not completely wrong, but it is wrong. But it's sort of a rule of thumb. Sometimes you see people write about it as if it's an exact thing, which it's not. But you can define sort of an effective dimension, which is the maximum of the actual dimension and 2D over alpha. And very roughly speaking, you should think of the model, the long range model, behaving kind of like a short range model with this dimension. Okay. Now I want to stress again, that's not really correct. But it's quite close to being correct, like numerically. And so, and in any case, it does capture the right intuition that decreasing alpha is kind of like increasing the dimension. Okay, so by considering these long range models, we can get into this situation where we have kind of a continuum of dimensions. And in particular, we can start talking about like rigorous versions of these expansions in the dimension that I was mentioning before and things like that. So for example, this is exactly the approach that's taken in this work of Gordon Slade that I mentioned, where he does rigorous expansions around the upper critical dimension for the spin ON model. Okay, but just to warn you that this is not really correct. So just something to be aware of. Okay, so one way that we understand these models surprisingly well is that we actually know that there are no infinite clusters at criticality under fairly mild conditions on the model. Okay, so Noemberger proved in 2002 that if alpha is equal to D, then there is no phase transition. That there is no infinite clusters at the phase transition. In other words, the phase transition is continuous. Okay, and this is actually a pretty mild condition because, you know, if you're in, for example, 3 dimensions, this is saying alpha is smaller than 3. You know, this is alpha being 2.9 or something is actually a fairly light tail on these. It's like if you did a random walk with this same jump kernel, then it would be converging to Brownian motion. It would have finite variance. It would have a finite 3 minus epsilon moment or whatever. You know, it's really not that restrictive. So in particular, as will become clear in a minute, this theorem applies to models which are conjecturally in the same universality class as nearest neighbor percolation in 3D. Of course, proving that they are is another matter, right? But still, I think it's really interesting and something that has received less attention than I think it ought to have from the community. Okay. Now, on the other hand, so what we would believe is that in dimensions 2 and higher, you always have this continuous phase transition. But in general dimension, Noemberger's result is optimal because it's a result of Eisenman and Newman that if you're in 1 dimension and have alpha equals 1, you actually get a discontinuous phase transition where the infinite cluster emerges all at once at the point of phase transition. Okay, and you know, it's an interesting thing that many of the proof techniques that one has for this model, it tends to be that the important quantity in them is just the ratio of alpha to D. So coming up with techniques that don't only see the ratio and actually see the actual value of D seems to be kind of a serious obstacle one has to get through to understand the larger values of D, like the larger values of alpha when D is not 1. Okay, so one thing to mention is like the relevance of this alpha less than D condition. So one way you can see that there's a clear geometric interpretation of this, which is that suppose you take 2 boxes of side length n and you put them at distance n from each other, then when alpha is smaller than D, there will be a large number of long edges that are open between these 2 boxes. When alpha is equal to D, there'll be like a Poisson number, like an order 1 random number. And when alpha is bigger than D, you'll have no such edges with high probability. Okay, so Okay, so not only do we have a reasonably good understanding of this basic question about the continuity of the phase transition, there are also surprisingly simple conjectures from the physics literature about how the exponents depend on the parameter alpha, which is this describing the decay of your long-range kernel. Okay, so okay, so first of all, we have a similar picture in high dimensions that we have mean field behavior. Okay, so except there's now a different meaning of high dimension, and it's actually exactly when this effective dimension is bigger than 6. Okay, so it's when either the dimension is strictly bigger than 6 or alpha is less than d/3. Actually, what I wrote here is a bit wrong. So it turns out one interesting thing here is that actually if d is equal to 6 and alpha is 2, which is d/3, it turns out that even though this is like a boundary case, there's an interesting thing that happens where it actually has exactly a mean field behavior, even though it's on the boundary. It's quite different than, and this is something that was studied by Chen and Sakai. Okay. Okay, and these things have been understood again with basically the same kind of techniques as the nearest neighbor model, the lace expansion. Okay, so what's the prediction that I mentioned? Well, basically, it's the following idea. So, in fact, let me don't look at what I have written already because I'll spoil it for you. So here's the idea. So suppose, let's start by looking at the 2-point function, right? So remember, this means that at criticality, okay, now I have beta c, probability x is connected to y. It's supposed to decay like this. Okay, now here's the idea. So first of all, the idea is if alpha is really big, so this means the probability x is connected to y by an edge, decays very quickly. I mean, like a big power, right? So plausibly, once alpha is large enough, the model should just have the same critical behavior as the nearest neighbor model. Okay, so the idea is that if you're way over here, this graph should just fixate at whatever its nearest neighbor value is. Okay, now on the other hand, if alpha is very small, so small alpha makes the model behave like it's high dimensional. Okay, so that means, from our general conjecture that the critical percolation in a high dimensional setting should behave like critical branching random walk. Okay, but now it's not the branching random walk. It's not like the simple random walk, right? It's this long range random walk. Okay, so if alpha is small, that random walk isn't going to converge to Brownian motion anymore. It's going to converge to a Levy process. Okay, and it turns out that for a Levy process, when alpha is less than 2, the Green's function looks like this. Okay, so if you believe that for small alpha it behaves like a branching Levy process, you should just get this line, x equals y, just the 45-degree line. Okay, now what the conjecture is that, in fact, these are the only 2 parts of the curve. So if you want to find the whole curve, you just join them up continuously. You just extend them until they meet. Okay, so this is the conjecture. And this is basically due to a physicist called Sack from the 70s who made similar conjectures. Well, I mean, I should say that more like gave non-rigorous arguments for these behaviors. He was working in the Ising model, but again, these conjectures are things that are supposed to hold very generally. Okay, so to go back here, so there's a few comments I have on this. And sorry, I'll try and get to at least some of my results before I run out of time. Hopefully this has been an interesting discussion anyway. So one thing is that there's actually another value of alpha which is important, but which you don't see on this curve. So there's this what's called the crossover value, where you switch between these two parts of the curve. But in fact, there's another special value, which is d over 3, which is where mean field behavior kicks in, right? And so if instead you were to look at the graph of delta, which is the volume tail exponent, it should have these 3 pieces in say 3 dimensions or something, where first, when alpha is very small, you're in the mean field regime and delta is 2. Then there's this middle part where it's supposed to be this rational function d plus alpha over d minus alpha, and then it's going to fixate at whatever the nearest neighbor value is. So again, these are both like simple pictures. Of course, there is something complicated hiding here, which is the value of alpha c, or equivalently the value of the nearest neighbor exponents. But other than that value, which is some very complicated number, that's a very simple picture. Okay, and the way I've been understanding this is that, so you have these kind of 2 phases, and these represent 2 different strategies for growing a large cluster, which are competing with each other, and one is winning in one phase and the other is winning in the other. So when alpha is small, what happens is the most efficient way to grow clusters from one scale to the next is that the large clusters in one box and the large clusters in the other box merge to each other via bulk-to-bulk connections, these long edges that go from kind of the middle of one box to the middle of the other. Whereas in the large alpha case, the most efficient way to grow is through boundary-to-boundary connections between the 2. Okay, so roughly it's this competition between these 2 strategies that's giving you this transition. Okay, so, and of course, you can also think about this at the level of sort of universality classes and scaling limits and stuff like that, which is that when alpha is bigger than alpha c, the long-range model should belong to the same universality class as the nearest neighbor model, whereas if it's smaller than alpha c, it should be something else, okay? And one way I've been understanding this is that when alpha is smaller than alpha c, the long-range Euclidean model behaves like the hierarchical model, okay, which hopefully I'll have a tiny amount of time to tell you about. Okay, so I've been kind of obsessed with these conjectures for a few years, and actually the first thing I did about this was back in 2020, and this was actually before I knew about these conjectures. So what I was doing then is just trying to prove some power law upper bounds on the critical behavior, not really particularly concerned about getting the correct ones. And so, okay, it's not particularly important what these are, but, this was the first thing I did, just proving some power law bounds. And, I had to write the introduction to this paper. I thought I should research properly what the conjectures are and so on. Then I found actually, these bounds they're actually not so bad. They're kind of reasonable. And then I learned about all these conjectures, and then, wanted to try to actually maybe prove something. And so, so actually for the long range model on ZD, we now have some fairly good results. Of course, there are some parts of the conjecture that are probably really hard. Like there's this implicit thing about being in the same universality class as the nearest neighbor model one. Anything about very large values of alpha is probably going to be very hard, because it gets back to the difficulties that you have in the nearest neighbor model. But what we know is that, in fact, this simple behavior here, which is this straight line on the left-hand side, is always an upper bound on the true value of the exponent. Okay, so in particular, if you look at the average of the 2-point function over a box, it's always bounded by r to the minus d plus alpha. Okay, so that corresponds to this green line here, which is an upper bound on this true exponent curve, which is in red. Okay, and like just a month or two after I put this paper on the archive, there was a follow-up work by Baumler and Berger in Munich, and they proved that a matching lower bound holds for alpha less than 1. So that's this purple curve. So in particular, the model with alpha less than 1, we actually exactly understand this exponent now. Okay, now the way I've drawn it here, this looks like a pretty small part of the graph, but one thing I'd like to stress is that actually in one dimension, this is the whole curve, right? Because when alpha is bigger than 1, you don't have a phase transition anymore. So I think this is really cool, and I don't think that there were any other results like this for any model, really. I mean, this is really an exact determination of the exponents in the full range of values of alpha, which is kind of like changing the dimension. So in particular, this certainly includes models which are not mean field, right? The mean field behavior kicks in below d/3, so 1/3 in one dimension, and then you get all these different low dimensional behaviors as well, which we exactly understand at least this one exponent for. Okay, and in 2 dimensions, the mean field behavior is at 2/3, so you get this 2/3 to 1/3 interval of models where we understand the exponent and they're interesting and that they're not mean field. Okay, but so I should say there's still a lot that needs to be understood about these models, even in this part of the curve where we know this. So for example, for this other exponent delta, you know, I was able to get like a slightly better upper bound on it, but it's still, we still don't know how to even just prove a one-sided bound. Johannes and Noam have a similar thing for alpha less than 1, they get the sharp lower bound. But there's some interesting things to do there. And essentially, this is what I have been able to do for the hierarchical models. And it turns out that as well, so there's a couple things to say here. So one is that actually the way that I proved this upper bound, and to an extent this is true for the lower bound as well, is really by like comparing the Euclidean model to the hierarchical model. Okay. And I think this is a really interesting thing that hasn't been done before. So, you know, using hierarchical models to understand critical behavior is something people have done for a long time, but sort of only as a toy model. You know, it's not been like, let's understand the hierarchical model and then actually really use that at the level of proofs to understand Euclidean models. It's more like, let's understand the hierarchical model, and that will tell us what we should be proving about the Euclidean model, right? It's more like a guide. Whereas this is really like taking the hierarchical proof and like forcing it to work for the Euclidean model. So obviously I'm running out of time to really tell you anything about that. Let me just say, for the hierarchical model, basically the idea is you do long-range percolation, but instead of doing it on the lattice, the standard lattice, you do it on what's called the hierarchical lattice, which has a lot more symmetry. And in particular, it's much easier to do renormalization group analysis in the hierarchical setting. Whether or not you're doing it rigorously, it's certainly much easier to do it rigorously, but it also makes non-rigorous renormalization group analysis much easier as well. That basically the idea is that the boxes in the hierarchical lattice have this kind of exact recursive structure where the box at the next scale is formed by taking some copies of the box at the previous scale and setting all the interactions to be the same between different copies. So you don't have, there are no boundary effects in the hierarchical lattice, it's only bulk, right? So that's partly why you can understand this small alpha Euclidean thing as acting like the hierarchical. It's like small alpha is when the bulk to bulk interaction is the most significant one. In the hierarchical model, you only have bulk to bulk interaction. And in the nearest neighbor model, you only have boundary to boundary interaction. So that's kind of why you can understand these two phases in that way. So let me just sing. I'm not sure what time I was supposed to go to actually, but let me at least just tell you the results, which is that for this hierarchical model, I've been able to exactly understand the volume tail, in fact, many other things as well, but including the logarithmic corrections at the critical dimension, which is 3 alpha for these long-range models. So in particular, okay, you have the mean field 1/√10 behavior in high dimensions. You have this exponent, this d minus alpha over d plus alpha. This is the same rational function we saw in the graph earlier in low dimensions. And at the critical dimension, you get 1/√10 times log n to the 1/4. Okay, and one interesting thing to notice is that this is not the same log correction as is predicted to hold for the nearest neighbor model in 6 dimensions. Okay, now really the proof, this is like one like nice thing you can extract at the end, but the proof really tells you a lot more than this. It really gives you so one point of the proof is it's kind of implementing something like a renormalization group analysis of percolation, but which is really working with percolation, right? There's no, because we don't, seriously, it's not like, oh, you convert to some supersymmetric, blah, 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 and then you do like a more standard renormalization thing. It's really like you want to work all the time really just with percolation directly and try to kind of reformulate the tools that people use like more in this setting. So I think that's hopefully something people will find interesting here. Another thing is that it very clearly, you see in the proof why there is a distinction between these low dimensions, high dimensions, critical dimensions. And again, sorry for overrunning, but let me just say a little bit about that, which is basically that there's really like a qualitative difference in what the clusters look like in these different regimes, which is ultimately reflected in these different asymptotic tails or whatever. But you know, there's really a much more conceptual way of thinking about it, which is basically that when you're in low dimensions, what happens is all the interesting behavior in the model is sort of stored in the like few biggest clusters. So if you look on some scale and I tell you what all the 10 biggest clusters look like, whatever, that's enough for you to answer most of the questions that you'd be interested in to a high degree of accuracy, you know, just knowing the first few largest ones. Okay, they just carry all the interesting information in some sense. On the other hand, in high dimensions, that's not the case at all. Like it's not that there's a few big clusters that are kind of carrying all the information. It's more like you have this kind of soup of a large number of sort of large-ish characteristic size clusters that together carry the interesting information. Okay, and this fact that you have a large number means that you have various like concentration properties that you don't have in low dimensions. It makes the dynamics when you scale behave very differently as a result of that concentration, and you start getting all these like Gaussians and stuff coming up. And at the critical dimension, it's kind of similar to high dimensions. It's just that you get like a logarithmic number instead of like a polynomial number, and that this basically means that the analysis is very similar to high dimensions, except that because the error terms are quite large compared with what they are in high dimensions, it makes everything much more delicate. The second order corrections to things are quite large, and those end up manifesting themselves as these log corrections to scaling, because you have these quite large second order corrections to how things scale just across one scale. Okay, so I think I'll end there. Sorry for overrunning, and thanks for your attention.
Thank you very much, Tom, for the very nice talk. I guess it's time for questions from the public. So maybe I can start with the question. This is about more the introduction of the talk, when you were mentioning the relationship between percolation and renormalization group.
Yeah.
And okay, you have been talking about critical percolation, but if you allow me to go outside the critical regime, it seems to me that there's also another way of thinking about renormalization in percolation. It's like adding obstacles, right? Something like that. So because you know, people have been wondering in the physics folklore that morally doing this decimation transformation should amount, morally very and wavy, in changing the temperature, basically. So there is this kind of folklore picture of flowing towards the critical point.
Yeah.
Yeah, if I'm not mistaken, there is some work in which you can actually interpret the presence of obstacles as a change in the critical critical probability for percolation, right?
So I'm not completely sure what you mean by obstacles.
Yeah. Mm-hmm. So I think the technical term should be something like enhancement, essential enhancement.
Oh, like right. That. Yeah. Right. Yeah, so I should say that so there's a lot of work that's been done on renormalization approaches to supercritical percolation, which I think is more along the lines of what you're asking about, maybe. So, you know, there are many things where you want to say that when you do supercritical percolation, the infinite cluster looks very much like the lattice that you started with, right, at large scales. And there are, this is something that has been done a lot, and I think, like, for example, if you wanted to do the Ising model on the percolated lattice with p close to 1 or something like that, there are good tools for doing renormalization in that way. And the main relevant name there is the Grimmett-Marstrand, right? So they in their paper, I mean, the theorem is something else, the main theorem, but really what they showed is that you can kind of do renormalization of supercritical percolation. But the thing is that it's not really the same kind of thing as like the sort of Wilson style renormalization group. It's not a tool for analyzing critical percolation, really. I mean, for one thing, these methods are quantitatively extremely poor as you approach the critical point. So typically this is something people don't really bother doing, actually, but there was a and it's not really clear because the arguments are quite complicated to start with, but there was a paper by Domenico Pan, Cosma, and Tassion, I don't know, 6 years ago or so, where they tried to make this Grimmett-Marstrand style renormalization quantitatively as sharp as they could, and you get something. It gives you estimates on near critical percolation, but they're very far away from what is expected to. And they don't tell you anything about critical percolation. So I think, for example, they look at the correlation length, and they show that if you're epsilon away from PC, the correlation length is at most like e to the 1 over epsilon or something like that, you know. So this is interesting, and there are things where it's useful to have like any reasonable bound, even if, but you know, of course, the true behavior should be some power. It's just that the thing is that this Grimmett-Marstrand style renormalization, it's really, you want to say that you want to basically show that you're flowing to the trivial, like, supercritical fixed point, right? That's more like what these techniques are for. Whereas actually at criticality, that's not happening, right? Or at least conjecturally, it's more like you're well, actually, I think we know that doesn't happen. I mean, even if we don't know that there aren't infinite clusters, we know that the infinite cluster doesn't look like ZD. So yeah, it's just a very different thing. Yeah, so basically the way I do it in the hierarchical case is you keep, the nice thing about the hierarchical thing is you can keep track of much less information because of all the symmetry when you rescale. So basically what you do is you look at the sum of squares of all the cluster sizes and the sum of cubes of all the cluster sizes and the sum of force powers of it, and so on. And then basically this whole thing evolves as this kind of infinite dimensional dynamical system. And you try and understand, you look at the expectations, in fact, and you get like a infinite dimensional, like deterministic dynamical system. And you try to understand how this evolves over one scale. And it is something like a Wilsonian, at least, you know, you're not looking at Hamiltonians because you don't have them, but morally the kind of analysis that you have to do, it's really like, you really want to think of critical behavior in terms of this dynamical system. In that sense, it's very much in the spirit of the renormalization group.
Okay, thank you. Any questions? So, okay, so maybe, again, it's not really a question, it's kind of something that reminded me about something else. When you were talking about comparison, the comparison of a lattice model, let's say, to a hierarchical model.
Yeah.
This reminds me also the case of the XY model in let's say Z2, with long range interactions, decaying as 1 over distance to some power alpha. And yeah, and there is this. Okay, I sponsor very much this paper by Kunz and Pfister, in which they prove that there is a first order phase transition actually in the long range case, exactly doing this kind of comparison of magnetization at the origin with respect to the one of hierarchical model, which has some.
I see. Oh, cool. That's interesting. I wasn't aware of that paper. I guess I should say that the thing that is very classical is arguing about the existence of a phase transition by comparison to the hierarchical model. I mean, this is actually what Dyson was doing in his first paper, where he introduced hierarchical models back in the 60s. And I guess if you want to show that you have a first order phase transition, I can imagine that, I mean, I don't know about that paper, but I can imagine it's a bit more similar to like showing that you have a phase transition in some sense. It's like, well, I don't know how that proof works, but you know, it's you can get some quantitative control on like where it happened. Anyway, that's interesting.
Okay.
What's the
yeah, I can give you the reference. Yeah,
okay,
I can send you the paper. Yes.
Nice. Yeah.
Questions from the public? Okay, so if there are no more questions, I would like to thank again Tom for accepting our invitation, and remind you that this was the last talk for this year, and we are resuming back next year with a lot of interesting news. Thank you very much, Tom, again.
Yeah, thanks for having me.
Yeah, have a nice afternoon, everybody.
Cool. Yeah, thanks again. Bye.
Thank
oh no, I guess I should advertise we have the last Percolation Today talk in an hour and 15 minutes. Anyway.
So people switch
Percolation talks today.
Yeah, for the interested ones, switch Zoom account to Percolation Today. I guess it's in 1 hour, something like that.
Yeah, it's at well, 3:30 UK time, 4:30 French time.
Cool.
Yeah.
Allez.
Bye.
Good afternoon. Bye. Bye.